Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're gonna talk about futures of motor. So let's dive right into it. Now, why the heck I'm talking about motor, so to say? It's kind of boring, but here's the deal. It's the core of our civilization, flat out. Everything runs on it, everything, and I mean everything, even quote unquote diesel engines, they run on it. So flat out everything runs on it, from your lift, from your water pump to every Tom Dick and Harry thing. Flat out everything runs on it, and everyone also runs on it. It's not something like, oh, that engineer uses that, oh, that industrialist uses. No, every Tom Dick and Harry. Your life would not exist the way it does, simply because if we did not have the induction motor, we did not had water pumping. And like, can you imagine human civilization without modern water pumping? So let that sink in. Like, flat out, it does not matter if you are from India, Pakistan, Nepal, Bhutan, Australia, Antarctica. Your life runs on motors, flat out. And industry, flat out. Like everything else, you may be able to go back to, like, Stone Age, but industry will disappear. It will not go back to Stone Age. It will poof, go disappear. And large locomotion flat out relies on that. You may think these diesel engines are quote unquote diesel power. All they are doing is they are running a generator, electrical generator from that diesel power, and that electrical power is driving motors, and that is actually moving the damn thing. So it's core of our civilization, flat out, very important technology. Now, what do we want? Let's say, what is motor? Fundamentally speaking, it taking one form of energy, converting it into rotational energy. So what do we want out of that? Well, we want YOLO amounts of torque. Torque is the key here. Think of it this way. Why the heck your car has gearbox? Simply because it does not have torque at right RPMs. So your engine have to be a certain RPM to give its optimum torque. Let's say around 3000 RPM. But here's the deal. Let's say you are going down slowly. You are just slowly moving. Your car cannot do that. Fundamentally, it cannot do that. So you have to tone down the RPM. How do you do that without reducing the torque? You employ a gearbox. So gearbox takes the higher RPM. It's almost like acting like a transformer. Same way like you take high voltage with low ampere and make it into low voltage high ampere. You are doing the exact same thing with transmission. Now we don't want that, and that's why electric cars do not have gearboxes. They do not need it. So because the motor has YOLO torque, it's like if it's running on 10 Newton meters of torque, it's gonna have 10 at very low RPM or even high RPM. So fundamentally, it does not need any sort of gear arrangement. So that's first requirement. It must have YOLO amounts of torque. Another aspect, because it's a thing that we use for years to come, or sometimes decades, or sometimes even one whole century, it must not have grinding parts. Basically, the amounts of parts that are rubbing against each other, they should not be too high. Think of it this way. The reason why your petrol engine or diesel engine does not does not last very long without maintenance, simply because they have parts rubbing on each other, like metal piston running on metal cylinders going. So basically, if your lubrication fails, bye bye. So we don't want that. We don't want this kind of situation. We don't want like smooth rolling roller bearings, nothing more than that. So we don't want brushes. So there are motors that they have a lot of good characteristics, but they have brushes. We don't want that. Especially we don't want that. Now, high efficiency, because energy is not unlimited. Even if you are running energy, getting energy from clean sources, let's say solar and all that, would you rather waste that energy? Because you have to understand that waste heat energy is just that heat. So think of it this way. You have a ceiling fan. That ceiling fan is 50% efficient, and let's say it's consuming 100 watts of rotational. It's giving to its blade, it's giving 100 watts of energy. If it's 50% efficient, that means consuming 200 watts. That means it's a 100-watt heating element. So you don't want that. You don't want your air conditioner to act as a heating element. So fundamentally, we want high efficiency. Now again, there are laws in nature that will not allow us to go to 100%, but damn close is good enough. Like 90 plus, 80 plus is bare minimum. Like we shall not go below 80. Now it should be manufacturable. There are many designs. You go to patent office, you go to like fancy motor designs and concept. There are thousands of designers. Like, we're gonna solve this world, we're gonna change this world, we're gonna save this, everybody, everything is awesome. Except, can you manufacture it? No. That's the whole thing. Everything is possible in a lab, nothing is possible in a factory. So be very mindful. When you see some design that is like too complicated, too extra hoo-ha, let it be. Simply because it has to be manufacturable. There are many designs that came and went simply because nobody could manufacture it. So, and another aspect is, inherently it should be simpler. Like, it should be so simple, like connect a plug, it works. No brain, advanced logic and all that. Like, again, we would like to avoid it. And it should be cheap, because again, there are motors that can be manufactured, but they are so complicated that it costs too much and nobody buys it. So we have a very huge list of basically desires, so to say. Now let's come down to reality. That's our desires. What's our reality? Reality is there is no one motor that can fit at all. Flat out, nothing. No one motor that can do it all. So what we have learned the hard way, what we call, we have to use different motors. Flat out, for different tools we have different requirements. So power requirements have two factors, almost like watt. So watt could have two component to it, like voltage and ampere. You have same here basically in a motor system. So you have torque and RPM. So you can easily buy induction motors that are like, all of induction motors are more or less the same RPM. Why? Because if they are running on AC main powers, their RPM is kind of limited by the design. So most of them, let's say, are running at 1600 RPM. Here's the deal, one would be 1 kilowatt, another would be 10 kilowatt. How the heck, what the hell is changing? The torque value is going up. So these are the two requirements. Now on top of that, these are just two factors. Okay, that much oomph you want out of your motor, but you also have to think about size and power constraints. Think of it this way. Let's say there is induction motor. Basically you are using induction motor for your drill, power cord drill. Here's the deal, you will not be able to hold it. It will be too big. It will be too big, too bulky, and too heavy to lift it. So flat out, your drill that you have, like corded drill, they are generally universal motor. Benefit, they're cheap. Another benefit, they are very torquey. So that's awesome. They are more torquey than basically induction motor, and they are small, fundamentally small. Consequence, why don't we use universal motor in everything? It has universal in its name, simply because it has brushes. It grinds. It, like, you can literally take a drill and go and you will see sparks coming out of it, simply because of that. It has brushes. It physically grinds away. So these are very good for low term uses, and you need a lot of power density in small things like starter motor. These are awesome. But if you have doing something, let's say electric e-bike, where your power budget is limited, you cannot go like very inefficient on that, because universal motor, small sizes, they're only 30% efficient. Big ones can only achieve 50 to 60%. So flat out you cannot do with that. So people use BLDC motors. BLDC motors are very efficient. They can go as high as 90%. So different tools, different requirement, different size constraint, and there are other aspects also. You have to think of it this way. Let's say you want to use induction motor in your basically washing machine. Here's the deal, your washing machine has different RPMs. Induction motor by design, they do not like to change their RPM, like, again, unless you are changing the frequency, which will require you to have another complicated electronics. So that's the reality. We have to learn it this way. It's like, okay, can we do this or that or that? So what are the current kinks, basically things that are allowing our modern world to function right now? So we have Daddy, induction motor. Basically induction motor is the brainchild of Nikola Tesla, and it's so mind-bogglingly awesome, so amazing. It has no moving parts, no grinding parts. Basically you can actually watch more than 100 videos of people repairing motors from around 1800s, and those motors, the only thing that has been worn out is the bearing. They just replace the bearing, and if the coil has not been destroyed, everything is awesome. They just keep running it. There's nothing to wear down. Specifically if you are talking about 3-phase AC induction motor, they are self-starting. They don't even need capacitors. Like, flat out, you don't have to do anything to them. They're like YOLO. Awesome. You don't have to think. It's just like, just put it there, maintain the bearings once in a while, everything is fine, everything is dandy, go YOLO. So this is the basically backbone of our industrial reality, and water pumps also, and water is very important. So that's the first. And then somebody came along, it's very early on, but somebody came along, it's like, hey, we want to have single phase power also. Single phase had a problem. It's like, you cannot start an induction motor on single phase. Like, if you can spin it, it will go YOLO, but how the heck you gonna spin it? So in early days, we created some weird technology known as shaded pole motors. Now this is a single phase self-starting motor. So you can take a normal induction motor and run it on single phase if you can add a capacitor, a secondary coil, and a trip switch. You can understand that is kind of complicated thing. So shaded pole motor also exists, and you can see them in your microwave oven, your exhaust fan, basically wherever you have live equipment, basically running on 220 volt or 1020 volt, wherever you have something like that, and it's like very small, low power, quiet kind of thing. Generally they are shaded pole motor. They are very simple. They also run for centuries. They have nothing else to wear down. So they are very small but quiet beast. Then we have universal motor. This tool allowed us to make powerful things like washing machine, like power drill, like chop saws. All those things are running on universal motors. Now that's the first difference. You can see low level tool and high production tool. Production tool will never touch universal motor. So if you are drilling by yourself once in a while, universal motor is good for you. But if you are running a factory, you can't do that. So first thing people will buy is a drill press. Why? Because drill presses uses induction motor, and it can keep running 24/7 without wearing down too much. So that's you do that. And what about portable electronics like motors? Like your portable drills, they are running on DC motors. Now DC motors are also very simple. Specifically the brushed DC motor, they are very simple. You just connect positive and negative, go. Very simple, very elegant, They are awesome. And in around, if you watch old videos of around early 2000 electric vehicle department, most of people were using this puppies. Why? They have insane amount of torque, as in torque that will make modern motors look like chump change. It's like, bro, like the motors, the conversion EV dude who were doing the conversion, they were destroying shafts, like motor shaft that was designed to handle, motor shaft as in like the gearbox, it was designed to handle 1000 horsepower, and the motor is like, nope. So flat out, very simple, idiotically powerful. Like, think of it this way, like it's in palm, it fits inside a palm your hand, and somehow it has the enough energy to drill through a brick wall. And someone, if you gear it down, you can even drill through metal. So fundamentally, these are powerful beast of fundamental reality of our existence. So first new champ in the town is BLDC, Brushless DC Motor. Now think of it this way, all we are doing is, brushes are doing is like switching from point A to point B, let's say coil A to coil B. All we are doing, somebody figured out, hey, we have solid state relay, meaning we can change electricity, basically turn electricity on or off using semiconductors rather than requiring a physical switch. So somebody's like, hey, let's throw away the brush and let's use normal electrical logic, like logic gates and circuits and transistor, MOSFETs, IGBT and all those jazz to actually do the switching. Benefit, no brushes, so your thing will not wear down. That's awesome. Another aspect, permanent magnet gives us a lot of oomph. Permanent magnets are always very oomfish. So benefit of that is like you have very high amount of starting torque, and because if the torque is very curve is very well adjusted, it is very efficient. It's like very high efficiency, like flat out on labs. Like, I'm not talking real world example, but if you want to push it, like you can almost achieve around 98% efficiency in real world. So again, it will be too ludicrously expensive, but it can be done. It's very efficient, but does require advanced control. It's not something you just plug a battery, double a battery, and it's gonna work. No, it's not like that. So fundamentally that, but does allow a lot of torque. That's why modern washing machines are utilizing this, and they come with like ludicrous warranty, like 10-year warranty on that motor, because there is nothing to wear down. Like universal motor, that puppy will wear down physically, it will wear down. Here there is nothing like that. And it also allows one thing that is a very big drawback of induction motor. Induction motor do not like to change their speed unless you can change the frequency, and that is a complicated thing. So here, because it's directly running on a complicated advanced circuitry, you can change the RPM very reliably, which has advantages in specifically one industry known as air conditioning unit. All modern air conditioner unit are slowly switching to BLDC, simply because right now our air conditioning units are like on off. Basically they are PWM. Side effect of that is like, if you are doing it at like 28 degrees Celsius, it will be like, oh, it's too cold. Oh, is it even on? It's too cold. That happens because it only can go to 16 degrees Celsius and then like wait for room to heat up. Okay, 16 degree to cool it down too much is like PWM, not very efficient product, because motor cannot slow down. It goes full power all the time. So BLDC allows them like, calm down, compressor is like, relax, just put 40% of your power. That can be done with BLDC. So BLDC is becoming a slowly growing into our world. And not to mention, BLDC is an old technology, but it was only used in computers. And if you know the price of old computers, you know for a fact how computer industry could afford it. But now it's coming more into mainstream because silicon technology has caught up to this. And heck, in India you can find BLDC ceiling fans. So BLDC is slowly starting to creep out into our reality. Then we come to the new hotness in town, switch reluctance motors. Now this puppy will replace induction motor. This is the next big thing. Everything is there, but here's the deal, it's just an induction motor. You don't have to think about it. And like, heck, you can literally buy conversion kit for your existing induction motor, especially if it's from a reputable brand or large company, especially big ones. You can just swap out the core and it will work. Like, you can understand that it's fundamentally an induction motor. But problem with induction motor is the way induction motor works is like, it has a magnetic component and an electrical component. Now magnetic flux or field, that's rotating because of your AC power. It already has a frequency, so that's awesome. But here's the, why the heck this awesome field will do anything to rotor part? Why the heck rotor will rotate? Why the heck rotor will give a damn? Here's the magnetic field and electrical fields, they are intermingled to each other. You can always extract one from the another. We do that in transformer. Like, you can look any transformer diagram and you're like, okay, coil 1 is here, coil B is here. How the heck power electricity is going there? It's insulated. Everything is insulated, well insulated. Heck, we put oil into it to insulate it. So how the heck electricity is going from one to another? It's not. Magnetic field is jumping. So that's core principle of your current induction motor. That's why it does not require brushes. It's like using the magnetic field to carry energy. That energy is being dumped into what we call a squirrel cage. It's shorting it out. Shorting it out means it creates a loop. Basically, it's a complete loop. Now, complete loop, there is a magnetic field, there is an electrical energy. Electrical energy creates its own magnetic field. Now you have two opposing scenarios. It's like, okay, we have to rotate. So it works, everything is awesome, but here's the you created a shorted electrical field, flat out you created a short circuit. Fundamentally that heats up. Now that was a problem with early Tesla models, is because they had a motor, it was heating up. Like you can find induction motor that are YOLO powerful, again they move locomotives, they are more than powerful. But here's the thing, you look at 1000 horsepower motor that's like is giant, like it's huge. And they run on like some ludicrous voltages, like 12 kV I have seen the highest. So you get the point, they're ludicrous, but how the heck you make it small? You can make it small without any issue, but here's the, it will not sustain because the core will heat up too much. So in Tesla model they actually drilled through the shaft, and they had a liquid cooling the core itself, rotating core, they had to cool the core. So somebody came up with the idea, what if we remove the electrical shorting part? Let's just remove it. So you will be left with laminates. Now these laminates act as a permanent magnet if exposed to a magnetic field long enough. Now here's the, all our normal induction motor have been slowly switched to what we call variable frequency drive. So basically the frequency, the rotating magnetic field frequency, we have been successfully slowing it down. It's like, okay, so your air condition, you can go to BLDC, or you can just employ a circuit that allows VFDV to normal compressor motors. So especially big motors, there are like 100 horsepower, 500 horsepower, those generally run on VFD, variable frequency drive. Benefit of that, you can switch down the frequency and RPM will slow down. So somebody came up with the idea, this rotor will rotate with a magnetic field if it's magnetized long enough. It's like, if you give it time, if you switch too quickly, it's like, I can't do anything, it will just vibrate. And it's inherently non-starting. It fundamentally is not technically even a motor, it's like electromagnet, it's not doing anything. So because we have such an advanced electronics semiconductor industry, somebody figured out, like, what if we actually tell it, go to point A, go to point B, go to point C, go to point D. That's what we are doing. So basically, if you remove the electrical generation part, it will still work without brushes, but it inherently does not have any starting torque, inherently does not have anything. So you have to treat it as an electromagnet that is spinning. So we can do that with very advanced basically microcontroller, microprocessor and all that jazz. Then why the heck we want to do something this complicated? I'm like, we have 100 years of experience with the induction motor, so why do we want to change it? Simply because it allows 10% more efficiency, because there is no shorted electrical path, that electrical resistance goes away flat out. It's almost behaving like a permanent magnet motor, and permanent magnets are expensive. This uses normal laminates which are very cheap. So I specified in our motor department, like, there is no point of having a motor that you cannot manufacture. This can be manufactured on cheap, and you can understand that right now there are kits that you allow you to swap out the rotor of your old motor with a new one. So fundamentally that's why people want to do that, but you have to understand this needs super advanced drive system. It's all about the drive. It's not even a motor. I don't know why the people are calling it a motor. It's like a freaking electromagnet. You're like, okay, go to point A to go to point B, go to point C. It's an electromagnet. So will it change everything? For civilian use, hell no. For industrial use, absolutely. Because in industry, when you are talking about hundreds of kilowatts of power, saving even 10% of that is a very significant, big enough deal. So this will change industry over time. So this was my presentation on basically the future of motors. I hope you liked it, learn from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.